This is a multimedia presentation that is a supplement to the Sustainable Country Living book. That dovetails with Chapter 9 in the book, which is Alternative Energy Microhydro. So today's topic is microhydro power. This little illustration shows the general idea. You have water coming down a creek. You go upstream and you collect some of that water. It goes down a pipe called a penstock. Then there's a hydropower system that uses that energy from the gravity of that water coming down the pipe to run a device that will spin and then generate electricity. And then the water, which is still completely the same water, it doesn't use any of the water, it just uses the energy in the water. The water then flows back into the creek. The resulting power can then be used to charge batteries and to help out with your house power. So how do big hydro systems work?
It's not just the lights that brighten our city streets at night. Electric power is so essential today it's hard to imagine life without it. Electricity is produced by a number of methods, one of them being hydroelectric generation. Conventionally, a dam is built to hold a large reservoir of water. The energy created by water falling from high to low levels turns the blades of a turbine. This rotates a generator to produce electricity.
So big hydroelectric systems are usually with dams of either a large earthen dam or concrete dams. There are both. That dam does two things. It pushes the water back and collects it like a bank for future use. It also elevates the level of the top of the water, and then that adds pressure for the difference between the top of the dam and where the power generator is to push the water pressure down to make the generators work in the dam. And then that converts that energy into electricity. Now here's an illustration showing it. You've got a dam, and in this case, the water intake is partway up from the bottom. It's not at the very bottom, or you might get sediment in it. And it's not at the very top, because if a reservoir of water goes down later in the summer, when it hasn't been raining and runoff, then you want the intake to be at a level that can capture whatever water there is. So that water then goes through a penstock and then spins a turbine, which powers the generator, which makes electricity. The water then goes back into the river, and the power is taken by long distance power lines to be used elsewhere. So I'm going to show you several examples of microhydro systems. These are ones that are small enough to do a house as compared to the big ones we just looked at. In this case, it's in the state of Colorado, and this is an off-grid property and a microhydro system. He actually has over the years made two different kinds that we'll see here in his video.
Over the ages, man has used water power to simplify many physical tasks. The most common application of hydropower has been on a huge industrial scale, which has resulted in the centralization of power generation with enormous dams and reservoirs. When you hear about renewable power, you generally hear about technologies of large wind farms, which are again centralized power, generating on a massive scale, and huge solar arrays, which are of the same utility-grade scale. I have said before that the movement of water on Earth is the largest movement of mass on Earth, and something we would be wise to capture. When hydropower is mentioned, it is usually said that the resource has already been maximized. There is seldom any mention of microhydropower as a decentralized and viable means of harnessing electric capacity. My own journey with microhydropower generation began in the early 90s. We were fortunate to locate a remote off-grid property in Colorado which had abundant water flowing over it. In the last 26 years, we have harnessed microhydropower with two very different yet very similar systems. The first system we installed in 1996 was supplied with spring water collected from two separate springs and transported in nearly a mile of 4-inch pipe. It was a direct drive system because we had adequate pressure, and it also fed a pond where we could raise trout. After 18 years of use, the springs began to lose the abundant flow due to an extended mega drought in the west and the installation of a pond which may have directed water away from our underground aquifer which fed our springs. In 2013, we decided to make a substantial investment to upgrade the system by moving to a creek which ran on a piece of land which we purchased in the mid-90s. The new system would have a far greater output of power utilizing the original Pelton turbine and generator we had purchased in 1996.
So you can see that industrial scale hydroelectric dams are centralized. The commercial, renewable wind farms and solar farms, those are also centralized and commercial. But water is abundant as a natural resource, and microhydro is a good option because it can be done on an individual scale and is not centralized through a power company. In this case, in Colorado, this individual had a spring-fed microhydro system originally from two springs, and then later switched when the springs started to dry up a little bit. Then they went to a creek-fed microhydro system that fed the same equipment from the original, and so this has been going on for 20 years. This particular off-grid property is in Washington State, and in this case it's a whole community. Stehekin is a little town in central Washington State that's up against the mountains in the Cascade Mountain Range, and has lots of water, and this town's been around for a long time, has about 100 people in it, and they are off-grid, so they have been generating their own electricity for many decades, and it wasn't until recently that they made an agreement with the regional power company to have a mutual handshake kind of arrangement. They're still off-grid, but they're getting the help of the municipal regional power company. So here's a drawing of the Stehekin power source. They have, like I say, about 100 people. And then in the summer, because it's a tourist area, the population increases greatly. Could be 3 or 4 times as many. The hydropower plant was built in the 60s, and it's a 130 kilowatt unit. If you look at the drawing, they also have as a backup a secondary source of a diesel generator. And then in an emergency, they have 2 other diesel generators. So in general, they're able to keep up with the hydroelectric, being able to make enough electricity to provide for the whole community. In this particular case, you wouldn't call this microhydro because it's not for one house. It's a pretty big operation, but it's been done successfully for a long time. Now, let's take a look at homestead microhydros. This is a particular video clip that's going to show you the steps, the major steps in making, establishing whether your property is a place to do it, and if so, how to go about it.
Welcome to our step-by-step guide on setting up a hydro generator to power your homestead. Are you ready to harness the power of water and save on your energy bills? Let's get started. First, determine the ideal location for your hydro generator by analyzing the water flow and head at your site. Remember, the higher the head and greater the flow, the more potential energy you can generate. Next, select the right hydro generator for your needs, considering factors like power output, efficiency, and durability. A Kaplan or Francis turbines are best for low-head applications. Once you've chosen your hydro generator, it's time to install it. Safely secure the turbine and connect it to the power system. including batteries, inverter, and control panel. Now that everything's in place, it's time to test your hydro generator. Monitor the energy production and adjust to optimize performance. Enjoy the benefits and don't forget to maintain your system for long-lasting efficiency.
So in this particular demonstration of the steps, step number 1 is to determine the feasibility and whether you have an ideal location to do this. This requires a couple of things to consider. One is how consistent is the water in the creek? Is it year-round or does it dry up in the summer? Because that's important if you're going to figure out if it's going to provide your needs when you need it. Now, if you have a hybrid system where maybe you have microhydro and you have solar, it could very well be that the solar in the summer, when the creek might be real dry, you might get enough off the solar, and then in the winter, when it's raining and snow melt and things like that, when the solar's not doing as well, then the microhydro could possibly be an alternative to the little bit of solar that you get in the winter. So you need to determine its feasibility. Is it practical to do it? And is the property that you're on provide that? In general, you need flowing water going downhill. There are some exceptions, but the ideal is to have flowing water going downhill. So you need to calculate the head. Head is the term used for what is the vertical distance between the intake of the water pipe, and called a penstock, and where it comes out at the generator at the bottom. So for instance, you can figure this out by going to Google Earth and go on the property and put a mark on where the intake would be and where the outflow would be, and it will tell you the difference more or less in feet. You could do this to property you haven't even bought yet. You're considering buying it, and you could go and figure out the head by using Google Earth and walking the property. The next thing you need to do, you could also do when you haven't owned the property yet, and that is to figure out how many gallons per minute you can get from that water source. So you would go up to where the intake would be, and then you take like a 5-gallon bucket and then a stopwatch, and you would scoop that bucket under there, wait till it's full, dump it, do it over and over, and when a minute is up, count how many 5-gallon buckets you did and divide by 5, and that would give you how many gallons per minute. And so obviously the higher the head and the more flow that you have, the more power you can generate. Step number 2 is to design a place to collect the water at the beginning. This is called an intake. And this water needs to be clear in that if there's debris like leaves and things like that, you want to have a screen of some sort that prevents debris from getting into the penstock. And so we'll show some examples of that. So you'd need the water to be clear, it'd need to be free of debris. And the intake ideally would be a self-cleaning intake, and I'll show you one after a bit. And then when the you want to have water that's free of bubbles and air. And so if you have a lot of air and turbulence in the water, then as it goes down the pipe, you're kind of cushioning it with the water. The other thing is that the penstock going down the hill needs to be fairly flat without any up and down dips. So in some cases, people will make a bridge over a little swell area to make sure that pipe is not dipping up and down, because what will happen is if the pipe is not consistently going downhill and it has a swell in it, then you could get air trapped in it, and that would make the production of electricity by much less. Okay, step number 3 is to install the penstock. That's the pipe going from the intake down the hill. And like I say, it needs to be continuous. It's not to have any low spots, and it should be protected. Keep in mind, if it's a pipe laying on the ground or on some kind of little bridge, You might have damage from trees falling or animals stepping on it. In the case of a white PVC pipe, if it's out in direct sunlight for a long period of time, it could deteriorate the quality of the pipe. So it would be ideal to bury the pipe all that distance, but it's not always possible or not always financially practical. So some people will use PVC pipe, the white pipe, say a 2-inch pipe, lay it on the ground and make it go where they need to go. Another option is poly pipe. That's the black pipe. It might be an inch pipe or 1.5 inches, and it comes in a really big roll, and you just roll it out and lay it on the ground. Step number 4 is how you're going to make electricity. Now that you've got the water collected at the top and it's coming down the hill in this penstock pipe, you need to select the best type of generator for what you're trying to do. And then you have to consider how much head pressure do you get, how many gallons per minute, and then consult with a company or 2 or 3 that sell hydro generators, micro hydro generators. There are Pelton wheels, there's Kaplan, and there's Francis, and you can research these. The most common is a Pelton wheel, which is basically a spinning wheel with little spoons on it, and the jet hits the spoons and makes it spin, and that makes the generator go. But depending on your head pressure and your gallons per minute will play into which of these types of micro hydro units you'd want to purchase. The other thing to consider too, is it going to be alternating current or DC, direct current? And this will factor in the size of wire that you would use, how far you need to travel to take that power to your house. There again, you'd want to get some advice on that. You will see in some of our examples, they'll have an alternating current style generator, and then it'll have maybe 3 wires coming off it in 3-phase, and then it'll go through a rectifier that converts it to direct current with 2 wires. I don't want to be too technical, but you need to get advice. Once you know the head, how many feet are you dropping, and probably how long is your pipe, and how many gallons per minute. With those numbers, you can then go to someone who sells and understands these different options, and they can advise you, and also how far the wire has to go to get to your house. So that will dictate what kind of a generator you're going to get, and then you're going to design how you're going to do your powerhouse, where this is housed. Is it going to be out in a box? Is it going to be in a building? Is it going to be, just open with a little roof on it to keep the rain off? You need to figure out how you're going to do that. There's all kinds of ways to design a powerhouse. And the last step is to start it up and try it out. You want to test the results. You want to see how much it's working, make adjustments. And remember, these are a moving part, functioning machine. So occasionally you'll have to check on it and possibly do some maintenance and adjustments. Now we're going to look at a couple of examples of applications where there's basically no head at all. The first one is like 3 feet, and the other one has no head. In other words, no drop in the water, and yet you can still make some electricity.
Recently, there's been a growing interest in smaller scale methods, using slight differences in the levels of flowing water. Underneath this bridge over a river in Tokyo, a small-scale hydroelectric generator has been installed. Although the water drop is just 1 meter, this generates enough power to light the bridge. Ena is a city in Gifu in central Japan. Masaya Sumino, an engineer at a metalworking factory here, has developed a revolutionary water power generator that's gaining international attention. This is Sumino's ultra-small water power generator. A 1 meter by 28 centimeter casing encloses the spiral blades of the turbine. flowing water has energy, and I always thought it was a shame that we weren't fully using this resource. That's what inspired me to come up with this concept for utilizing unused energy from nature. Weighing just 18 kilograms, this is the first ever generator of its kind that can be easily carried by one person. It's already being used in roadside irrigation channels to power streetlights and for electrifying fences to protect farmland. To spread his message about water power, Sumino often gives presentations to primary school children like these. Today, he'll show them how to generate electricity from a small river in their school grounds. Okay, now I'm going to put it in the water. His generator works even with the gentle flow of this tiny stream. The spiral blades are angled, so they rise slightly towards the upstream side. A 15-centimeter high metal plate blocks the stream. This makes the water run over the top of the plate and flow down through the spiral blades. The force of the water on the blades turns the turbine to generate electricity. This concept works anywhere there's flowing water, even if it's very shallow. Three, two, one, now! That was amazing! Such a small machine and it made electricity. In Japan, schools are often used as evacuation shelters during disasters. This device could provide emergency power. Sumino's generator promises to transform life in remote areas of the world that still lack power. There are many places where individuals or whole areas have no access to electricity. If we can provide them with the means to make their own power, they'll be able to change their lives. That's my hope. An ultra-small generator that could provide environmentally friendly electricity for any place on Earth where there's even a slight flow of water.
So in this particular case, we have a low-head application in the form of the lighting of the bridge. It only dropped a yard and 1 meter, and it had enough generating power to light all the lights on the bridge. And then this ultra small power generator is portable that can go in a creek that has no head. And this spiral design is lightweight. It can be used for emergency power and in remote locations. Now we're going to look at a low head, high flow micro hydro system. This is one that doesn't drop a lot, but it and isn't actually using that, the fact that it drops, but it's sucking it out of the pond and creating power because there's high flow, because there's a lot of water moving.
Behind me is a pond that is several feet deep, and there is a dam on this side, which drops approximately 8 feet from this point here down to the rock. And then there is an additional drop from that rock down to the bottom for a total of 15 feet. So you can see there is a couple of 100 gallons coming across this all the time. And here is the intake to his unit. He's got a screen cage that prevents debris from entering into the pipe. And then he's got a 6-inch pipe elbowed down into the water here. See if I can move you across here without dropping the camera. Pipe goes over about 6 feet and then 90s around this little concrete pillar. And that, you can see here, goes over to the turbine. And this is all 6-inch pipe up to the turbine. There is about an 8-foot pipe dropping down, another 90 which heads over here, and there's going to be a demonstration of how this unit is turned on here in just a moment. And from the edge of the white pipe, it then upgrades to an 8-inch pipe, creating a vacuum with the Venturi effect. Because the other end of this pipe here is sticking down into the water, the siphon has to be created to get the water from the top of the dam into this pipe here. To do that without some kind of suction device would be quite difficult. You would have to have a port here with a shutoff valve and pour water into the pipe to produce that siphon. But with this design, Bill has got a shop vac that will create a negative pressure and will pull water over the dam for him without much work at all.
As soon as I turn this on, that turbine will begin to turn within 5 seconds or less. So get ready to watch that, and here we go.
There we go, starting to spin.
Now I'll just shut this off. The air bubbles will get cleaned out of there in quite short time.
This is a 3-phase AC unit. So you can see he has the 3 wires of the AC coming into this joiner box here. And he has 10-2 wire that's ground contact. He's using the grounds of this wire to take the 3-phase to the house.
So this thing creates so much suction that, as you can see now, after this thing's been running, we started it up about 10 minutes ago, the flow rate over the top of the dam is significantly reduced, and the suction here is just powerful. You can see below the creek how much water is still running through the creek and who's not coming over the dam, and it's all going through this system. So the gallons per minute rate, I don't know, but it was all of what you saw before.
The wire run from the turbine to his house is 100 feet. So with AC, he's losing very little power from the turbine to the house.
So what's unique about this design is it's a siphon system because it's sucking the water up out of the pond, and as compared to others where it's catching it and gravity's making it go in. They have to siphon it, and then the larger pipe at the bottom creates a suction called a Venturi effect, and kind of like an hourglass is an illustration of Venturi. And then in this case, it's an alternating current 3-phase generator, and they're running that 3-phase wiring AC all the way to the house because it's only 100 feet to get to the house. Now we're going to look at a very small 1 kilowatt micro hydro system. You can see it's pretty simple, and it's not in a building or anything. So even with this very simple generator, it's producing a significant amount of power. This gentleman has a YouTube channel, and he goes around to different sites, and the one you saw earlier was him, and there'll be 2 more from him. But this one is in North Carolina. It happens to be his house, and he's telling his journey of finally being able to create his own micro hydro system.
It's been a long time dream of mine to have a micro hydro system that supplements power to my house, and I'm happy to say that that dream has finally become a reality. I'm Seth with the Land to House YouTube channel, and this is my journey into micro hydro. The journey started in the early parts of 2020. I went up the mountain and got some basic calculations. My flow rate here is around 30 gallons a minute most of the year. The distance from my source down to where I wanted the turbine was 1,100 feet. The head pressure from the source down to the turbine is 150 feet, which gives me roughly 65 psi. One nice thing about the microhydro system is how it self-regulates. You notice I had plenty of overflow coming out of my 55-gallon barrel, but if it hasn't rained for a while and the flow rate drops down, the water will slowly start shrinking down the pipe until it reaches a point where the pressure pushing out the nozzles is equalized to the pressure up the hill, and the flow rate will maintain at that point. So it's still able to make power even though it doesn't have the full penstock of water. So it's pretty cool. Now there is a point where it drops so low that it just flows out the bottom and it doesn't have enough force to keep the turbine spinning. But for most of the year, it has somewhere between 50 and 100 watts of power coming off the mountain. Now, if I were to crank open more jets, I can get up to 400 watts, but then I risk losing all the water in my penstock and not making any power. We've just reached the end of the 1,100 feet of penstock, and we're here at the microhydro turbine. I'll show you what this looks like and go through some of the iterations that I have been through to get to this point. And I'd also like to tell you about a couple things I'd like to change for the future. Just like with my other connectors, I have a barb fitting on the poly pipe, and I've used several of these hose clamps to keep more of this unistrut on here, and that prevents this from breaking free. It then swaps over to PVC pipe and goes first to a T with a pressure gauge so I can see what the pressure is running. I do have a relief valve over here if I need it for anything. I've got this ball valve here which will turn on or off the turbine to allow water flow. And then it goes into this box. Now this box has made several iterations, and I'll show you one of those over here. This little wooden box over here is the first attempt, and it worked somewhat, but was not allowing enough exit water to go back down to the creek. And so I stepped up my build game to make this all PVC version, and it has done well, except I need to water seal this a little bit better on this side. You can see it's got a leak over here. One of the cool things about this box is that it has a clear base on it, so you can see the water falling down into this base and then going back down to the creek. I can open up the lid here. I don't know if you could hear that or not, but when the wind hit the turbine, it slowed things down a bit. This turbine is from Langston's Alternative Power. He built the box and geared up the motor so that it would work well with my flow rate and head pressure. It also has the PVC pipes going around, and I have 4 different nozzle sizes that will spray water into that Pelton wheel. Currently, I only have one nozzle open, and that's a 3/16, and that's generating close to 100 watts.
So in this case, the microhydro system wasn't feeding his whole house, but it was supplementing his power needs for his house. And he started first by measuring the gallons per minute and analyzing the seasonal consistency. In other words, is this going to be the case year-round, or is it going to have a dry spell in the summer? And measure the distance from the source to the generating air end of the pipe, and then also calculate the head. So you've got 3 calculations: gallons per minute, the flow of the water, how long the pipe is coming down the hill, the penstock, and calculating the head, the height, this vertical height from the intake to the outflow. And his system included an intake, a penstock, pipe, a pressure gauge, a shutoff valve, a box that housed the generator, and then the generator was built by the manufacturer to match his specs of the head and the pressure and the gallons per minute. And in this case, it had 4 jets, of which at that moment he was demonstrating it, he was only using 1 jet. The more water that you have, you can use more jets and get more power. So that's North Carolina. Now, the same guy traveled to western North Carolina to show this system.
I'm here in the mountains of western North Carolina to take a look at a micro hydro system that is producing over 500 watts of power. This is feeding an off-grid cabin, and I wanted to show you the whole system from intake all the way down to the electrical system. The box behind me is the beginning of this hydro system. It's called a Coanda screen, and it is allowing water to flow over and be sucked in while keeping debris and other things out of the system. So the creek right now has about 200 gallons per minute flowing, and only about 110 gallons of water are going into the system. That allows the creek to continue flowing while pulling some of the water out for the hydro. In order to direct the water into the Coanda screen, a small concrete pad has been built to capture the water from these two culvert pipes. The water makes its way down here and then is channeled into a little concrete sluice here and directed over the Coanda screen. Now the water here is moving pretty quick. A few rocks have been placed right here in front of the screen to slow the water down so that it flows nice and softly into the Coanda screen. You can see this Fernco coupling takes the water through a 90-degree T and then heads down the creek in this direction. The next portion of the hydro system is the penstock, and that is the pipe that's going to carry the water from the source all the way down to wherever your turbines or turgo Pelton wheels are located. So the penstock is important to have both big enough to support the amount of water you need and to limit the friction loss, and it also needs to be air-free. And that means this pipe needs to be facing down the whole time and not have any up spots that could hold an air pocket. Because anytime you have an air pocket, it's going to reduce the pipe's ability to carry a full flow of water. I just walked down to the end of the penstock where the permanent magnet alternator, or PMA, is resting. This is the powerhouse that's generating the electricity to be sent to the house. So how this is working, the 50 feet of drop or head pressure in the penstock is producing about 22 psi of pressure. That is then sent to nozzles that point down to the cups or spoons hooked up to this. It's called a Pelton wheel. That is basically pushing that wheel around very quickly and turning the motor to allow electricity to be made. Let's step down here and take a look at this PMA. First of all, we have a large ball valve which allows the system to be turned off for maintenance. It has this massive union to allow this whole system to be disconnected. And so it goes from 4-inch pipe here, reduces down to 3-inch pipe. The homeowner has put a piece of glass over this unit so that you can see the moving parts, but it also keeps it dry in there. The static pressure of this system is about 22 psi. With the system running, it's dropped down to about 10 psi, which is still enough to produce somewhere around 500 watts. There is a gauge down here. Now the homeowner has locked down the turbine on this nice platform, and that prevents a lot of noise from happening because the system is locked down so tight. That 3-inch pipe skirts all the way around the unit and has keys that sweep in and reduce down to 2-inch. Now there are 4 nozzles on this system. 2 of them are 19 millimeter, 2 of them are 16 millimeter. Basically it's 0.6 and 0.75 inch. And that's what has the nozzles that go in there and hit that Pelton wheel that's underneath this spinning PMA.
So in this particular western North Carolina microhydro system, the water is funneled into the intake. The rocks slow down the water so that it's not so turbulent. And then the Coanda screen is the intake, and the purpose of a Coanda screen is to allow the water to get sucked in to the intake and not have all the water going there. It's also self-cleaning because the water that's not sucked in rinses the screen. It's quite a neat design, and it's pretty important to be able to have no debris and sediment in the pipe. The penstock is diameter sized to fit the amount of water available and the flow that results from that. So again, this is why these calculations ahead of time are so important, because that will help you know how much power you can make, what size pipe you need, how far it's going to go, how much pressure you're going to get, and so forth. And like he said, the penstock needs to be going downhill evenly. If it goes up a bit and down again, you're going to get an air pocket on the high side, and that will limit the amount of power that will come out the other end in terms of pounds per square inch. So you don't want any air pockets as a result of the pipe not being an even downhill flow. The system includes a generator enclosure, a building or a box in this case, a shutoff valve, a pressure gauge. In this case, he put the pressure gauge on the inside. The previous one, it was on the outside. Like the other one, it has 4 jets with valves to shut them off. And the Pelton wheel is the generator. And again, a Pelton wheel is a spinning thing with a collection of spoons on it. And the water jets push the water like a fire hose against the spoons and make the Pelton wheel spin, which is connected to the generator, which makes the electricity. So in this case, it's a permanent magnet alternator, which is nicknamed PMA. And that means it's making alternating current. That's the alternator. If you think about your car, if you're familiar with cars, engine compartment, modern cars have alternators and old cars had generators. And the difference is an alternator makes alternating current, whereas the generator can make direct current. And so in this kind of situation, if you're having alternating current and you want to store it in a battery, then it would have to go through a rectifier, which we'll see in some of these examples. So now we're going to take a close look at the Pelton wheel design.
For this unit, I've got a 2-inch input, which then reduces down to 1 1/4. Have 3 different ball valves, a 5/16 nozzle here, 5/16 over here, and then a 1/4 on the other 2 sides. The turbine is wired up to be 3-phase, so you have 3 wires coming out. On this one, I've got a rectifier here, so 3 wires, which comes down to DC. The motor spins like this up here and is connected to a Pelton wheel down below. So let's go ahead and flip this up. You can see it has a nice metal housing, so that's not going to be breaking apart anytime soon. I'll go ahead and flip this thing over so you can see what's going on in here. So here's the Pelton wheel. I'm assuming that's a 4, or I think it's about a 5-inch wheel right there. You can see the 4 different jets positioned to hit those spoons in the right position. Now, I believe these can be removed and replaced with different sizes, but I should be able to just turn off the ball valves whenever I don't have enough water to run this in full.
So in this particular case, PVC pipe is used and it splits and reduces so that by the time each nozzle jet has the pipe, it has taken part of that water that started out with a 3-inch, I think it was, and then 2-inch and 1 1/4. Anyway, it reduces it so that if all 4 are open, they're all sharing that amount of volume of water between the 4 jets. And then the water coming out of the jets hit the spoons on the Pelton wheel that makes it spin. Each jet has a shutoff valve that allows you to choose how many valves you want to have open, depending on, how much rain there is, the volume of water that might be available. And in this case, it's an AC generating 3-phase power. So it has to go through a rectifier, which converts that to 2 wires direct current, which then can be used on a battery. Now, we're going to end this with another example. This is a really strange one. This guy in Australia, I believe it is, figured out how to make an old washing machine become a micro hydro system. And he has very little money invested in this, and it lasted at least 6 years. So let's take a look.
Many ways to power this homemade generator. You can mount it on a windmill, bicycle, biogas motor, anything that will spin the shaft fast enough. I have a good supply of free water on my property, so I'm going to attach a Pelton wheel to the shaft, divert some of the water through a pipe, and the difference in height between the water intake and the Pelton wheel will create enough water pressure to spin the shaft, generating enough electricity to power my house. This is what you're looking for, a Fisher & Paykel smart drive. It doesn't matter about the size or model number, they're all pretty similar underneath. Tip it over and have a look underneath. You should see something like this. As long as the rotor turns freely and there's no side-to-side movement in the bearings, it should be okay to use. They're pretty easy to pull apart, just a couple of screws holding the top on. I'll take those out, flip it back, and you'll see a couple of wires there at the back. Just snip those. Unhook everything connected to the metal housing and just pull the tub out of there. All you really need to keep is the tub, the stator, the rotor, shaft and bearings. Everything else can go. If you're building a windmill or attaching it to a motor, you might want to cut the bearing assembly out of there, but since I'm using it for water, I'll leave it as it is. The motor will produce electricity with the factory wiring, but it is capable of making 400 volts AC, which is dangerous to work with and not very useful for most setups. Some people do use it like this, but I don't recommend it. Pull the rotor off the back and have a look for any chips or cracks in the magnets. If they're starting to break up, you might need to look for a new rotor. Check the stator wiring for any signs of corrosion or broken wires. And if you have a multimeter, test the windings for continuity. These small cracks in the plastic are nothing to worry about. Most of them have these. Now you're ready to rewire the stator. I made a detailed video showing how to do this, so have a look on my channel and you'll see it there. Using an old inner tube, cut out a circle around 6 inches in diameter. Cut a hole in the centre and slip it on the shaft. Keep it about a centimetre away from the rear of the tub. Now I'll attach the Pelton wheel to the shaft. You can get these on eBay for under $100. This one's been adapted to slide straight on the spline, but you can just bolt them on using a thread on the shaft. The water jet needs to hit the centre of the Pelton cups, so using a ruler, mark out where the hole for the nozzle will be cut. Use a hole saw to cut out where you made the mark. Now cut a hole in the bottom of the tub to let the water out after it's been through the turbine. Now I'm making a chute out of an old heavy duty piece of plastic and some screws. This will guide the water back into the stream. Using some 1/2-inch plywood, mark and cut out a cover for the front of the tub. This will add strength and stop water splashing out. A piece of perspex over the front acts as a service hatch and lets you see what's going on inside. Cut the hole big enough to pull the Pelton wheel out for servicing. Silicone sealant around the edges keeps it all watertight. It should be a nice tight fit. Push it in around 1 inch from the edge and screw it in place. Cut out a piece of foam for the seal around the service hatch. glue it in place with some silicone sealant. Before the silicone sets, I'm going to drill 4 holes around the edge of the perspex and clamp it down with 4 stainless steel bolts. Using wide washers to overlap the edge of the perspex. Now I'm making a cover to stop rain getting into the electrics. The plastic breaks down quickly in sunlight, so a quick coat of paint will protect it from the sun. The rewired stator, rotor and rectifier can now be bolted in place. The rectifier converts the 3-phase AC output of the generator into DC current suitable for charging a battery bank. Follow the link here to see how to make one. Plug the AC leads of the rectifier into the spade terminals on the stator and attach the rotor. Now the holes where the pump used to be need to be filled, so I'll just jam a couple of plastic bags in there. And it's done, all ready to start making free power. The water pressure is about 45 psi. At the moment it's making about 21 amps at 29 volts, which is just over 600 watts. If I put a bigger water jet on it, it'll make up to 900 watts, but I don't really need that much power this time of year.
Not everybody wants to build a project like that, but if this interests you, this washing machine apparatus that he made, I think he only spent about $100 for the Pelton wheel. And it lasted him 6 years. Another video he has, he goes out and figures out what to do to make it last longer. To find the videos, if this interests you, if you're a handy person and want to try this, just type in YouTube washing machine micro hydro, and you'll get to his channel, and you can see how he did the rewiring and stuff like that. But for those of you that don't want to do all that, you can buy a variety of off-the-shelf micro hydro generators. And I'm going to show you some starting at the cheapest. Here's one for $11. This is on Amazon. And it's a water flow generator, turbine generator, and it makes 10 watts at 12 volts. Here's one that's $175. And this is one that is low speed turbine, so this would be flowing water, not necessarily a lot of water coming downhill, and it's $175. And here's a better quality one for $149 that is a 500 watt mini hydro, 110 volt. It's made out of aluminum. And here's a similar one. This one's $208, 110 to 220 volts, 1000 watts. So we're getting more powerful as we go along. And here's another one that's the same category, 1000 watts, $280. And here's a 3000 watt one that makes 220 volts, and spins at 3,500 RPM. It's $600. And then here's one that is 3,000 watts, 220 volts, and it's almost $700. And this is some of the details. And then if you want to get really long term, here's one that's a 1 kilowatt water generator for $1,500. And here's one on the left that's $5,500, and it's a 1,500 watt, so it's a 1.5 kilowatt output. And then you can upgrade to as high as $9,900 to have the whole setup with the charge controllers and inverters and all that stuff. So we've gone from $11 to $1,000 range. And here again, what's important is that you analyze your property. You need to have water flowing downhill on your property to be able to do this. And the problem with micro hydro is most properties do not have this. Most properties are either not hilly enough or they don't have a creek on it. And what makes it even more complicated is some areas it's illegal to disrupt the creek, whether it's for a Pelton wheel or for a ram pump or some kind of thing where you're taking water and running it down a pipe, because some agencies are worried about the fish, some have water rights, et cetera, et cetera. So you have to, first of all, see if the property has the head and the gallons per minute to make it practical to do hydro. Then you want to decide if it's something legal in your area, or if it's remote enough, you might want to just do it incognito and just not be talking about it. But there are people that do it both ways. To be aware of new videos like this one, be sure to subscribe to the Preparing for the Time of Trouble channel. For more free videos and downloadable audio podcasts, as well as handouts, go to www.preparingforthetimeoftrouble.com. Topic categories include recordings of live seminar presentations, country living, sustainable gardening, homestead remedies, how to be self-sufficient when the grid goes down, wild edible and medicinal plants, hydrotherapy, and end-time Bible prophecies. To take advantage of these free resources, go to preparingforthetimeoftrouble.com.